Well, good morning, everyone. Welcome back. I have the great pleasure this morning of introducing our speaker, Maciej Capinski. Maciej did his PhD studies at Jagiellonian University in Krakow, Poland. He graduated in 2005, studied under the supervision of Piotr Gzinski. He's currently an associate professor in the Faculty of Applied Mathematics at AGH University of Science and Technology in Krakow. He's a member of the Distinguished Computer Assisted Proof and Dynamical Systems, or CAPD group, also based in Krakow. And Maciej's main interests focus on geometric and topological methods for computer assisted proof and in invariant manifold theory. He does a lot of work in celestial mechanics, and today he's going to tell us about some of his work on Arnold diffusion, especially with regard to celestial mechanics. So Maciej, thank you for being here today, and I'll pass things over to you.
Okay, thank you very much. Thank you to the organizers for giving me the opportunity to speak here. This is joint work with a number of people. So Jay is here as well. And so this is Marian Guidea, Jorge Gonzalez, Jean-Pierre Marcoyo, and Rafael de la Llave as well. What I would like to be talking about is outlined here in this first slide. So I will start with motivation. So like I will state the objectives. So state what is the problem, what is Arnold diffusion about, and I will try to do it in a simple context so that we don't get into very general statements, but kind of restrict to a simplest, let's say, setting that is possible. Then I will describe three methods that I think that are suitable for proving Arnold diffusion using computer-assisted proofs, because this is what we are interested in. So the first one, I call it Melnikov method, but maybe calling it Melnikov potential would be more accurate. So this is based on works of Teresa Ara, Rafael de la Llave, Amadeu de Shams, and of course co-authors. Also, the second method is the shadowing lemma for scattering maps. This is also originates from the same group, and I think it's also very suitable for computer-assisted proofs. And then I'm going to talk about an explicit construction. So this is based on work with Marian Guidea, and this method is based on covering relations, conditions, and horizontal disks. So I'll discuss the tools that are used for this. And I'll finish with an example, which is the restricted elliptic three-body problem. And maybe so that I don't forget, all my computer-assisted proofs are done using the CAPD library. So I advertise very highly. This is a fantastic tool. And if Daniel is here, thank you, Daniel, for all your willingness to answer all my questions regarding the use of the library. Thank you for your help. Okay, so let's start with the motivation. So the motivation is the following. I mean, this is going to be a very low dimensional talk. So we're going to work in an ODE setting, no PDEs. And the ODE is in fact written down here. So this is a form ODE where we have Q prime and P prime, and Q and P are two-dimensional. So we have a Hamiltonian system. So this H is the Hamiltonian before perturbation. So this is just from R4 to R. We have the perturbation term, which is G. And in fact, this perturbation is visible here, right? And this is from R4 times a circle. So this is a time periodic perturbation of a Hamiltonian system. So the system is written here, right? So we have H epsilon. And the important thing is that for epsilon equal to 0, this system is autonomous. So it's not time dependent. Okay, so this is the ODE that we are going to be studying. And one thing that I should start with is, I don't know if I would even call it a lemma. It's like an obvious fact that for the case, and this is quite important that this here I have epsilon 0, for the case when epsilon is equal to 0, the Hamiltonian value along the flow of a solution of this ODE that we have here, right? how do I highlight? Okay, so we have this ODE. So the Hamiltonian is preserved. So if I have a look at the flow, Q of t, P of t, then the Hamiltonian value of the Hamiltonian is not going to change. And here's like a proof. The proof is kind of straightforward. What you do is you compute the derivative of this expression. If it's 0, then it means that it is going to be constant, right? So you do the following, right? You have to do the partial and derivative of the inner function, right? And then you substitute. So for the case of epsilon equals to 0, this is the partial derivative of epsilon, and this is going to be just h, because epsilon is equal to 0, so this term just cancels out, right? So we substitute partial derivative of h with respect to t, minus partial derivative of h with respect to q, right? And we see that these terms they cancel out and we get 0. So this means that for the unperturbed case, the Hamiltonian is constant along the flow. So this brings us to our question and the main objective. So the main objective when one is studying Arnold diffusion is the following question. If I switch on the perturbation, so I choose some epsilon to be small and positive, does there exist a trajectory that would start with the Hamiltonian equal to 0? And I will frequently refer to this value as the energy. So if I say a word energy, I mean the Hamiltonian on the flow. So can I start with energy equal to 0 and end up with energy equal to 1? And this will usually take some time. So I'm denoting here t of epsilon, because this time is in fact going to grow as the smaller the perturbation, the longer we will need the time for the diffusion to occur. So the objective is to talk about methods that are going to answer this question. Okay, so we have our ODE, and I'm going to now make a number of additional assumptions, because I'm going to talk about the construction, and usually this construction involves normally hyperbolic manifolds, but I'm going to restrict to a very simple case. So I'm going to consider that I have a family of periodic orbits. So I have a family of periodic orbits, right? And each of these periodic orbits, and I have a subscript I there because the energy of each of these orbits is I. So I have a family of orbits with different energies. And I'm also assuming, so I'm making assumptions now for my construction. I'm assuming that the stable and unstable manifolds of these periodic orbits, that they intersect transversely on the constant energy level. And this is for the unperturbed system. So I'm making assumptions about the unperturbed system. And I'm going to say, okay, under which conditions do I have this increase of energy if I make a small perturbation? So here I have a picture. This is like a true picture from celestial mechanics. The periodic orbit is here very small. This is like a Lyapunov orbit. And we have the unstable manifold in green. We have the stable manifold in I don't know what this is pink, right? And these manifolds in fact intersect transversely. So the system, unperturbed system, is 4-dimensional, but we restrict to constant energy. So this is in fact 3-dimensional. So if I have a projection onto another coordinate, we can see that these manifolds, that they in fact intersect transversely. Okay, so if I have this transversal intersection of manifolds, usually if I choose a point of intersection, there's a homoclinic orbit for this periodic orbit. So I have a periodic orbit somewhere here. There's a homoclinic orbit that passes through this intersection of these manifolds. Sorry. And in fact, what I've drawn here, I think it's kind of representative of what happens. So I have a family of these periodic orbits right here, and I have a family of homoclinic orbits. So this is quite a typical setting in Hamiltonian systems. Okay, great. So now I can talk about the first method. So the first method is very classical, and it goes back to Melnikov. But I think that good references for this method are these two papers. The first one is a geometric mechanism for diffusion, Hamiltonian systems. and the other talks about geometric properties of the scattering map. So it talks a little bit more in depth on the theory of the Melnikov potential. So I'm not going to go into details of this. What I want to say for the people that would want to apply these methods to prove Arnold diffusion, what is actually required. So in order to apply these methods, what we have is we have two components. We have the periodic orbit and we have the homoclinic. Right? So I denote the homoclinic as phi I of t. Yes? And the Melnikov method, or the Melnikov potential method, boils down to the computation of the Melnikov function. So what you need to do is you need to compute an integral. And I'm not specifying, I could write out this function m. That's kind of a longish formula. That doesn't bring much to discussion. What is important is that this m is explicitly given in terms of h and g. So you have this, this explicitly given function, and you want to evaluate this function along the homoclinic as well as the periodic orbit. And there is a dependence on tau, which is in the time time dependence. And if you change tau, you obtain different values of this integral. And the method roughly says the following. So if this function m of tau has non-trivial zeros, then for sufficiently small epsilon, we will have changes in the energy. So we will have diffusion. So I think that this is a very good method for proving diffusion. It's a classical method for proving diffusion, and it's very good for computer-assisted proofs. It's kind of convenient because what I want to say is that homoclinic orbits can be established with computer-assisted proofs. So there's a large group in the audience here that knows exactly how to do these things. How to establish homoclinic orbits is not something that is profoundly difficult for many people here. And this is just a proof of concept, right? That people do these things. So I just chose two papers. And why these? I was kind of arbitrary in my choice. So I wanted to choose two papers with two different methods. So the first paper is by Daniel, and this one uses the covering relations and cone conditions. And this paper, by the way, does not restrict to proving homoclinic orbits. It proves a lot of other cool stuff. But the second method is a method that is based on the parametrization method. So the parametrization method can also be used to establish homoclinic orbits. And if you can compute the Melnikov integral along these orbits, then you've got your proof. And just as a proof of concept, this plot here, it kind of looks like it's done with a line, but I did like a computation with my student Natalia Vodka, and this in fact is a rigorous enclosure of this homoclinic orbit and the periodic orbit. If you kind of look closely, this is made of little cubes, right? So these things can be computed, but the Melnikov method has maybe certain disadvantages. So the disadvantage is that these results, they are for sufficiently small epsilon, right? So and one with computer-assisted proofs, one can do much more. So this is like a classical perturbation theory that says if epsilon is sufficiently small, but we don't know how small, then we will have diffusion. And another thing that I find a little bit of a bother in this method is that you need to compute an integral along a homoclinic, and this is a lot of work because you need to have a very good enclosure of the homoclinic, and doing this, approximating this integral is a little bit of work, and I found this to be a little bit troublesome, right? But this is a classical method that definitely can be applied in computer-assisted proofs. Okay, great. So this brings me to the second method that I want to advertise very strongly. And this method is based on the shadowing lemma for scattering maps. So I am assuming that most people here do not know what scattering maps are. So what I'm going to start with is I'm going to start with the definition of a scattering map. And the simplest setting for me is to say what would be the scattering map in the case for epsilon equal to 0. Okay, great. So what I'm going to do is I'm going to define the scattering map. But first, what is on this picture? On this picture, I have the same periodic orbit, but I made 2 copies of it. Yes, so it's one picture, right? But I made 2 distinct pictures for simplicity because will be adding some stuff here, right? So what I'm doing to define my scattering map, I need to choose a point X, which is on the intersection of the unstable and the stable manifold. So somewhere here is the unstable, somewhere here is the stable manifold. They intersect, and I'm choosing some point X from this intersection. And if I choose 2 points, X plus is here, and X minus, such that if I start with the flow from this X and move backwards in time, and I also move backwards from X minus, I'm going to converge. So this is like a specially chosen point on the periodic orbit. So if I flow backwards in time and I flow this guy, they're going to come closer and closer and closer to each other, right? And if I flow forwards in time from this X and I flow here, right? And this also wraps around the periodic orbit, they're going to converge. So these are 2 special points. And for these 2 special points, these 2 special points are in fact what defines the scattering map. So here I'm defining the scattering map. Sigma, that is my scattering map of X minus, is equal to X plus. So it's a kind of not a very natural construction. If you see it for the first time, it's a little bit on the artificial side because I started with some X, right? But in fact, I'm interested in the scattering map from X minus to X plus, but this is what it is. So for people that know a little bit more about invariant manifolds, I mean, I can say the same thing in a more clear language. So in fact, what I was saying, and I will say it again, is that in fact, this point X that is on this intersection of these manifolds is on the unstable fiber that starts at the base X minus. And I have the stable fiber with the base at X plus. These 2 fibers intersect. So the scattering map is a map that takes a point here on the invariant on the periodic orbit, assigns another point on the periodic orbit whenever the fibers intersect. So this is another way of saying it. And I started saying, okay, for epsilon equal to 0, I have a simple setting because I have these periodic orbits. But when do I need to have these periodic orbits? And the answer is no. I mean, in a more abstract setting, what you can have is not a periodic orbit, but a normally hyperbolic invariant manifold. You take a point on this normally hyperbolic invariant manifold, X minus. You take a point X plus, and if the fibers intersect, and there are some transversality conditions regarding this intersection, but I don't want to go into the details. So if these 2 fibers intersect, then I can define the scattering map sigma of X minus as X plus. Okay, so this was the definition of the scattering map, and now comes the punchline. So why is it useful, and why would I be interested in something like this, right? Because the sigma of X minus or this map sigma is not something physical. I mean, there is no trajectory that goes from here to here, right? Everything moves. Yes, so this scattering map in some sense is artificial. But there's a fantastic result, and I cannot advertise this paper strongly enough. It's a beautiful paper, fresh out of print, but the result has been on archive for quite some time. So this is a general mechanism for diffusion in Hamiltonian systems by Raphael, Tere, and Amadeo, and Marian Gidea, which says the following. So it says something like this. So if you have this trajectory, so this is this artificial trajectory for a discrete dynamical system created by the scattering map, right? So you have x k plus 1 is equal to sigma of xk. So this is something artificial. Then in fact, there exists a true trajectory of the system that shadows this pseudo trajectory. So the story is the following. Okay, if you can control the scattering map, if you can say where the scattering map leads, then you will also know that there exists a true trajectory of the system that is going to do something very close to this. And it turns out that if you take this method and you use it in the setting of the problem that I said before, right? So now I've added, I've slightly changed this lemma by adding epsilon here, right? Because we have the unperturbed system and we have the perturbed system, right? So these scattering maps, they are also defined for the perturbed system, yes? And in fact, what happens is you can do the following. This paper describes a Melnikov method type argument or perturbation type theory argument that allows us to control very well the behavior of the scattering maps after perturbation. So in fact, it's kind of, this leads to proofs that if you take the pseudo orbit from the scattering maps, then the energy of this orbit has to increase by a factor of epsilon with each iterate. So this theory gives you very good control. And in fact, if you know then that this pseudo orbit that is generated by the scattering map increases in energy, which comes out from perturbative methods, then you know that the system, the true trajectory, there has to exist a trajectory that is going to do the same. So this is fantastic. So you can use this lemma in kind of perturbative setting, but I think that this lemma, this shadowing lemma, shows a lot more promise if you look at it from point of view of computer-assisted proofs. Because in computer-assisted proofs, you can be much more explicit. You can, in fact, and all people working with the parametrization method know that you can have extremely good approximates on these unstable and stable fibers, on the unstable stable manifold. You know you can compute this to high precision and validate your results. What you can do is you can validate the dependence of these manifolds on the epsilon, right? So this this scattering map, in my view, is in fact very much computable for computer-assisted people. And what you can do is you don't need to use perturbation theory, but you can do this explicitly. So there is one paper that we have with Piotr that deals with this very similar problem. So that's this computation explicitly, right? This sort of computation. There is another paper that does the same, but in a multidimensional setting. And there is, in fact, a paper that is almost finished. So it's like, it's ready, but we're adding introduction and checking it. Right? So there's a paper with Jorge, Jay, Jean-Pierre Marcot, and this is like a mixture of this result done in a computer-assisted setting. So I think this is, I mean, generally my objective of having these slides was to advertise this shadowing lemma and the paper of Marian, Rafael, and Tere. It's a really very useful result for proving diffusion. Okay. So up till now, I mean, I talked about two methods where I was a little bit hazy on the details. And now I would like to discuss an explicit construction. And here I'm going to be a little bit more detailed. Yes? So, but before I talk about this explicit construction, I will talk about the tools. And people who have heard a number of my talks can switch off completely, because I'm going to talk about covering relations and conditions. These are I love these tools, and I will never stop talking about them. And they are very useful also in this context, right? So what is a covering relation? So, and let's talk about R squared, right? So we have a map, so we are in a discrete time case. Yeah? So many people will say, well, what is happening? We were supposed to talk about flows, and he's talking about maps. A link will come in a second, right? So I'm going to talk about maps here in this slide. So you have a box, right? I'm denoting it in 0. I single out two directions. So these are the so-called exit sets. They are in red. And I'm saying that I have a covering relation. So N0 covers N1 by a map F if the picture is topologically like this. So the exit sets, they map to two different sides, and this is important. It's not enough that they map outside. They have to go in across this box and in opposite directions. And the image of this box N0 does not match, does not touch the upper and the lower edge. And then I'm talking about, I mean, this is what I'm going to mean by saying that I have a covering relation. And this can be generalized to higher dimensions. Very nicely for me, throughout this talk, I'm going to just have one-dimensional unstable coordinate, always. So if you have one-dimensional unstable coordinates, you know what it means to go to the left and to the right, right? So the exit sets need to go to the left and to the right, right? And the rest needs to stay inside, right? So this is what the covering relation looks in R3. And in R4, well, these red things, they need to be cubes, right? Instead, but the picture is the same. So this is what the covering relations are. And the question, what are they good for? And the answer is, well, they are fantastic for shadowing. So there's a paper by Marian Gidea and Piotr Skaczyński, and there's a number of results, but one of the results there is a theorem which says that if you have a sequence of covering relations, so you start with N0 and you have a sequence of coverings in K, then there exists a trajectory that passes through these sets. So in fact, if you arrange them in a circle, then this means that you can go loop around forever. There's an orbit that's going to pass. In fact, the theorems there will also imply that there is a periodic orbit in there. But in particular, there's an orbit that's going to go in a circle for infinitely long time. Okay, great. So these are covering relations. And another tool that I'm going to talk, okay. So whenever I draw a picture two-dimensional, think about something higher dimensional, but with one unstable coordinate. Okay, so now cone conditions. So that's another tool that is useful for my explicit construction for the diffusion. I'm going to come to diffusion in a second. So what are cones? So let's see what is a cone. So maybe let's have a look at the coordinates first. So I said that there is one-dimensional unstable coordinate, and I denote it as x. So the first one is the unstable one, and the p, they are the rest. Yes. Okay. So I have a point that is represented by xp. So in fact, let's say here I have x star p star, right? So what is a cone? Well, these are the points that, well, let's just be vague. X is bigger than p, right? So this is this blue set here, right? So the difference in x is bigger than the difference in p. So it means that you're positioned horizontally. And this coefficient alpha, what is this alpha for? Well, this is just a constant, and the smaller the alpha, the sharper the cones. Right? So you can play with with how sharp these cones are. And we say that f satisfies cone conditions if the following is satisfied. So if you compute the image of a cone, so you have your C of Q, that's the cone in blue, you have its image here. So it's going to be attached at f of q, right? Because q is mapped into f of q. And there is another cone that is attached here. This is c of f of q. And what I want is I want the blue one to be inside of the green one, right? So you map cones into cones. This is what it means for a map to satisfy cone conditions. Okay. So unfortunately, okay, so you can do this in higher dimensions, right? So this is what it looks like, a higher dimensional cone. And the question is, okay, so why would one be bothered with, I mean, if one has covering relations, then one can already shadow the dynamics, right? This is very useful for computer-assisted proofs. So the question is, okay, why bother with cone conditions? And in fact, for the construction of leading to Arnold diffusion, you have to deal with the case where you do not have hyperbolicity. So covering relations are fantastic if you have one direction that is contracting, the other that is expanding. And then you can construct sequences of covering relations, get symbolic dynamics, do a lot of fantastic stuff. But as soon as you get central coordinates, so coordinates that are neither contracting nor expanding, you get into a little bit of trouble. And this is why I'm going to introduce another notion, which is the notion of a horizontal disk. It will seem completely artificial at this point, but I will show that this is a crucial component if you want to do shadowing, infinite shadowing in the setting when where you have a central direction. Okay, so what is a horizontal disk? So a horizontal disk is, well, it's a function. There we go. Here it is, h. So in our case, we have just one unstable coordinate. So this is going to be a function from 0, 1 to n, which is one of these boxes, right? And this satisfies this condition that if you project on the first coordinate, you have identity, right? And the image of this function is always contained in cones. So I think a good picture is here, right? So this first condition, whoops, how do I get, okay. So this first condition says that, okay, here I have h of x, so x has to be, right, so this is like a graph. So that's what this first condition says. And this condition says something like this. If I attach a cone at h of x, then this horizontal disk is going to stay inside of this cone. So this is what is a horizontal disk. And there is a great paper by Piotr Sliczyński that says the following, that if you have cone conditions and you have a sequence of covering relations, then in fact, if you take a horizontal disk in your first set, then it propagates as a sequence of horizontal disks through your covering relations. Okay, so maybe what do I mean by this statement more precisely? I think I will say what I mean precisely by doing the proof of this theorem, which sounds a little bit crazy, but you will see that it makes sense. So the proof would be the following. Okay, so I have my set N0, I take some horizontal disk here, right? So the image of this is, well, looks a little bit like this. Here I'm optimistic. I'm saying, okay, things don't wrap around. Okay, but more or less this is going to what it's going to look like. And this horizontal disk H1 that I depict here is in fact the restriction of the image of the first horizontal disk to the set N1, right? And okay, so why is this construction possible? Well, it's possible because of the topological alignment, but topological alignment in itself is not enough, because maybe from topology, things could really twist and turn, right? But if you have cone conditions that cones map into cones, then this image of this horizontal disk cannot get twisted, cannot get bent. So this is why this proof is possible, right? So this theorem says the following. If you have a sequence of covering relations, and if you have cone conditions, then you can propagate horizontal disks. And I will show in a second that propagating horizontal disks is very, very useful in terms of this diffusion construction. Okay. So now I want to get the next slide. Okay, great. So I talked about covering relations, cones, and horizontal disks, and now I'm coming back to my diffusion problem. Right. So this was a little bit while ago. So let's recall, what do we actually have? What have we assumed that our system does? So what we've assumed is we've assumed that we have this family of periodic orbits, right? These are these Li of t. Each of them has a given energy. This is before the perturbation. So what I've depicted here is I've depicted one of these periodic orbits, right? By this arrow. So I'm kind of, I mean, if I try to do a circle and do the same pictures as I'm going to do in a second, I would fail. So what I did is we need to identify this point with this point. This arrow is in fact a circle, okay? So on my picture, we should interpret this as a circle. And what I've assumed is that these manifolds, the unstable manifold and the stable manifold, they intersect transversely if I restrict to a constant energy level. So in fact, my system before the perturbation is 4-dimensional. I restrict to constant energy. This is a 3-dimensional thing. And in fact, this picture is representative of my assumption. But I have a family of these pictures. With each energy, I have a very similar picture. So this is like, these were the assumptions that I initially made. Okay, so these were my assumptions. And now I'm going to maybe introduce some notation for the coordinates. So I'm going to denote by x the unstable coordinate. So that's my coordinate x. By y, I'm going to denote the stable coordinate, right, at this periodic orbit. I is the energy, and well, okay, theta is the angle. So this is the angle along this periodic orbit, and there is also the extended phase space coordinate, because my system is non-autonomous, so it's in R5, right, after perturbation. And if you recall, I made my assumptions about covering relations, Kohn conditions, and they were expressed in terms of maps. So, okay, here comes the map, right? So I take the map. The simplest one to take is just the 2π shift along the flow of the 2π shift along the flow, right? This is like a 2π periodic orbit, so this is a very natural map to consider. Okay, so if I consider this map, I'm dropping this time coordinate, right? Because I have a stroboscopic map, right, along the flow. So the t is gone. So that's great, because I've reduced from a 5-dimensional flow to a 4-dimensional map, which is lower dimensional. So that's great. And in fact, in my picture, what I have is then the periodic orbit becomes an invariant circle for this map.
So this 2π is the period of the perturbation.
Yes,
right?
this 2π is the period of the perturbation.
But
But
periods of orbits, right?
no, this 2π has not. This is a very good question. It has nothing to do with the period of the orbit. So this 2π is the period of the perturbation. Yes. So this is why this becomes an invariant circle, right? So you have some rotation for the map, right? Okay, and for epsilon equal to 0, f of Li is equal to Li. Okay, great. So this is these are my assumptions that I've already made, and now what I will want to do is I will want to show an explicit construction using using covering relations and cones that will lead to diffusion. Okay, so for epsilon equal to 0, I have this family of periodic orbits. Energy will never grow because it's preserved. I switch on the perturbation. I want to have a construction that will lead to the increase in the energy. Okay, so how is this construction done? Okay, so I'm going to list a number of assumptions. And the first one is that f epsilon, so these maps, that they satisfy Kohn conditions. This is kind of natural because I have one direction that is the hyperbolic expansion of my periodic orbit, right? Even if I perturb the system, this is still going to be expanding, right? So Kohn conditions, they're going to hold after the perturbation. What I'm going to assume is I'm going to assume that I can construct a box M around the periodic orbit. So I'm in fact restricting to a certain range of angles, and I'm putting a box here around it, right? And this box has to be satisfy certain special conditions. So this box needs to be such that if I take a horizontal disk here inside of this set, then I need to assume that each horizontal disks can be captured inside of some set n0. Okay, So I can capture each horizontal disk in a set N0. And then the key assumption is that I can start with this N0 and construct a sequence of coverings. So I go from N0 to some N1, N2, up to Nk. And then I finally return after my sequence of covering to M and cover the larger set. Yes. So I'm going to make an attempt at drawing it. So this is, so I have my first set. So I compute its image. Then I compute N1, right? And then maybe I continue with this. You see, I'm kind of doing this, positioning this at the intersection of these manifolds, right? So you do like a horseshoe construction, and you should be able to return, right? So my assumption is that after some number of iterates, I'm going to return, and I'm going to have a covering of my final set, and I'm going to cover M. Yes. So important thing is that I am not assuming that I am going to start with N0 and I'm going to cover N0. Look, because here I'm treating the angle as the contracting coordinate. So this means that with each step of the way, I have to increase these sets, these H sets, right? So I'm only assuming something like this, that if I have a horizontal disk H in M, that I can enclose it in some set N0, and then I can return back to the M. So that's my assumption. And then I have a key assumption that says the following. Okay, if I take any epsilon bigger than 0, and I take any point X that passes through this sequence of coverings, then I am in fact increasing energy after such excursion. So these are the assumptions that I'm making. And here is the theorem. So this comes from a paper with Marian Gidea, and I will add references in a second. But if you have this set of assumptions, then the theorem says that for every epsilon, there exists some point X epsilon. There exists some possibly very long time, T epsilon, such that you start with energy equal to 0, and you end up with energy bigger than 1. Okay, so I know that this is quite vague what I've done here, right? Because I've drawn pictures, maybe there's missing some details. I'm not showing what happens on the energy coordinate, right? All of this is a little bit on the loose side. So I will return to this construction and I will discuss it again. But before I do it, I will make a number of comments. So the comments are the following. So these sets that I've chosen, these N0, N1, and so forth, they depend on the choice of the horizontal disk. So I have some horizontal disk, so if there's some curve here in this set M, I can enclose it in some different set N0 and do a different sequence of coverings depending on the horizontal disk that I choose. Another thing is that the length of this connection can also depend on the choice of my H. So I'm not saying, oh, you have to use the same number of no, you start and you can, the assumption is that you can do it for a given horizontal disk. Another, and I've already discussed this, but this is a big issue for covering relations, that with each covering, you have to increase, or at least if you choose it to do it the way I'm doing, you have to increase the coordinate theta and I. You need to increase the boxes, the size of the boxes in the central coordinates. So on this picture, you see, I ended up with some f of n0, and I made n1 to be wider on the angle. So this means that I will never be able to do this construction indefinitely for infinite number of iterates. Things will blow up. Okay. And another issue for my key assumption, right? Because I said, oh, okay, I have to have increase in this energy. How do I check it? Well, the way to check it is you just have to validate that the derivative of the change of the energy with respect to the perturbation parameter is bigger than C. So all my computations are C0. I just need to compute bounds on sets. This is the only assumption that requires a computation of derivative, and I do this computation of the derivative with respect to the parameter, and if I do a computer-assisted proof, nothing will stop me from taking a certain range of parameters. Sure, I can take a range of parameters. If I take a range of parameters, I validate this condition, then I have a proof for an explicit range of parameters, diffusion for explicit range of parameters of perturbation. Okay, great. So I will return to this picture in a second, but I want to outline one key issue, which is why am I talking about horizontal disks? Why am I not using omni-covering relations? Okay, so this is like I've devoted a single slide to it because I think it's an important thing. So the key fact about horizontal disks is that they do not grow along central coordinates. What do I mean by this? Okay, I wrote the sentence. This is the key issue that allows for infinite shadowing along the central coordinates. So this is really important. And what do I mean by the fact that they do not grow? So let's start with a really simple example, right? So this is a linear map. I have 3 times x, 2 times theta. So this coordinate theta is not even neutral, right? It's expanding, but it's weaker expanding than x, right? And here the horizontal disks, they will not grow. So let's see this. So what I have is I have a horizontal disk here, right? It's captured inside of a cone, right? So then if I take this picture here and I blow it up, multiply it by 3 on the x coordinate, multiply it by 2 on the theta coordinate, I will obtain this picture, right? So everything has grown, but in fact, in total, things got stretched, right? So this green cone, the image of this green cone is in fact tighter, right? Oops, I don't know what happened. Do you see? Sorry, I've lost some. Okay, I'm back. So this is why I don't like doing slide talks, because something is popping up on my screen. But I hope you don't see it, or. Geez.
Well, we'll just see it slightly smaller, but that's okay.
No, but I want to kill. Okay. Okay, so all right. So hopefully things are back to normal. So let's return to my map, right? Linear map, image of this cone, right? It's got expanded. So the original size. So this is the largest size that this horizontal disk could occupy in the coordinate along the angle. After the image, it cannot be bigger, right? So I don't know where the horizontal disk is going to go, right? But I know that it's not going to get bigger along the neutral coordinate, which means that I can capture it by another window, right, for the next iteration, right? So if I know that such window exists, yes, then I can do this sequence of coverings. So this is a very important issue, and hopefully it will be visible because I'm going to do now this same construction, right? But I'm going to do it carefully, right? So let's do it again. So what I'm going to do is I'm going to do 4 coordinates at the same time. So I have a picture XY, and on the XY coordinate, I have a very typical picture where we have the unstable manifold transversely intersecting the stable manifold, which will lead to kind of a Smale horseshoe picture, right? So this is a classical picture. And on here below, I have the coordinates I and theta. So I'm starting with a horizontal disk. So on the coordinate XY, it's this kind of shape. On the coordinate I, it's going to look like a little squiggle, right? But I know that horizontal disks cannot be too big on the neutral coordinates, right? So I'm representing, I don't know where it is, but it has to be a little bit, not too big, right? So I'm assuming that I can capture such horizontal disk in some set M0. And this orange kind of thing, this is my initial set M, right? So this is the range of angles that I'm considering. Okay, so then I do my first covering. So I compute f of n0, so it gets stretched, right? And it maybe gets a little bit bigger along the the remaining coordinates. Maybe there's some twist along the angle, right? Or maybe I get some errors from my computer-assisted bounds. It's a little bit bigger, right? So this means that I capture it in a set N1 that is bigger yet, right? But here on the XY coordinates, which are hyperbolic, the picture looks typical, right? That you would have in a small horseshoe construction, right? Okay, and then I continue with this, right? So this is the H set H1, right here. Then I propagate it again, right? So maybe the image of this N1 is something like this. Here it is on the neutral coordinates, right? Then I capture it in something that is on the hyperbolic coordinates. This is just a typical construction for correctly for covering relations. But here I take N2 to be bigger, right? And on the central coordinate, I'm always making things bigger, okay? And then I end up with the final covering. And this is great because this means that I've ended up with some horizontal disk, yes, that has returned to my initial set. So I came from here, but the question is, where did I get to? Yes. So where is this horizontal disk? Well, on the XY coordinate, it has to be positioned here. But on the I theta coordinates, I don't know where it will land. It will land somewhere in the green region, right? From my computation of the derivative with respect to epsilon, I know that the energy is going to increase. So if this horizontal disk is going to land up above 1, then it means that I've succeeded. I've proven diffusion. It's fantastic. I don't need to continue with this construction. But maybe it's landed somewhere else, right? Maybe it landed below 1, or maybe here, right? So let's say that it landed here, this horizontal disk. What do I do? Well, I know that here, I mean, this set, in fact, represents this set, right? So I ended up here. And from my assumptions, which I made, the assumptions were the following. If I have the horizontal disk, I can enclose it with some set N0, and I can carry this construction over, right? So, all right, I enclose it in some N0, do another excursion, right? I end up with some horizontal disk. It's increased energy, right? If this energy is above 1, fantastic, I've achieved diffusion. If not, I continue with the same construction, right? So this is the idea. In fact, the main thing is that horizontal disks don't grow, and you can do infinite shadowing this way, right? Okay, so this was it, and basically I don't have much time. So maybe just just to say that this works, right? So we've done one example, and in fact, the whole theory is described in this paper that I have with Marian. The paper is on arXiv, and we've used this method to prove Arnold diffusion in the planar elliptic restricted three-body problem for the Neptune-Triton system. Okay, so for the Neptune-Triton system, you have a mass parameter mu. So the normalized masses, so you have two parameters, mu and 1 minus mu. These are the masses. The mu is the mass of Triton, and 1 minus mu is the mass of Neptune. And we've used the explicit mass parameter. That is kind of what is observed in the real system. We chose the Neptune-Triton system because for this system, the eccentricity, we use the eccentricity of the elliptic orbits of these primaries of this planet and moon as our perturbation parameter. And in this particular system, they are small. So this is like the true eccentricity value. And we chose, okay, we would like to increase in energy by 10 to the minus 6. It looks like a ridiculously small number, but it is like a macroscopic number. Because everything is huge, right, in space. Yes, so it's not so small. And if you choose these particular parameters, the theorem says that, and this was a theorem that was proven with computer-assisted construction that I just described. It says that for every epsilon from 0 to the capital epsilon to the true eccentricity. So epsilon equal to 0 is the circular problem. Epsilon equal to 1.6 10 to the minus 5 is the true system. It says, okay, if you take any system parameter, any perturbation parameter from 0 to the actual 1, there exists a trajectory that is going to have diffusion of the given order. So this is the theorem that we've proven. And in fact, what we used is we used a homoclinic orbit. So this homoclinic orbit here, this is a Lyapunov orbit for the circular problem. So this is for epsilon equal to 0. Then I have a homoclinic orbit, and we used a sequence of maps, section to section maps along this homoclinic orbit. So these were our maps f epsilons. We moved from one section to another section, and we made this construction. Now, why do I think that this method is nice? The method is not nice because you can work with physical parameters, but that does not astonish anybody who works in computer-assisted proofs, right? I mean, we can treat concrete systems. Yes. The good thing is that you can take a whole explicit range of perturbation parameters. So if you do classical perturbation theory, usually the statements are for sufficiently small epsilon. Here you know that, okay, you know what the epsilon can be, explicit perturbation sizes. From our method, we get estimates on the diffusion time. I didn't talk about it, but they come out of the method. So we know what this T epsilon needs to be. We have concrete numbers. And I said that the change in energy is macroscopic. What do I mean by macroscopic? It's not really huge. So it's like a 1 kilometer distance between the Lyapunov orbits. So Lyapunov orbits that differ in the energy by this 10 to the minus 6 are in fact one kilometer apart. So you diffuse not very far, but it's something that is observable. It's not a ridiculous number. Okay, so maybe closing remarks because I have 1 minute to go. So I discussed a number of methods, right? So the first was like a classical Melnikov method. Then I think this is this shadowing for scattering maps is a fantastic method. It has great promise for computer-assisted proofs. And I think it's a little bit easier to apply than this explicit construction, because in the explicit construction, you need to get your hands dirty. You have to really do the construction explicitly, as the name says. But I think that these two methods are really great for Arnold diffusion. So I went into this method in more detail. So let's maybe emphasize things about it. I talked about 4 and 5 dimensional things. But in fact, the method is general. It's arbitrary Rn and normally hyperbolic manifolds and so forth. So it does not require these special assumptions that I talked about. The good thing about it is you can use explicit system, explicit perturbation size, and you get explicit estimates on the diffusion time. And in this paper that we have with Marian, we get a bunch of goodies that I did not discuss at all. So they are under the line here. What we in fact prove is that these orbits that diffuse in energy, they can diffuse also up and down as well. So we have symbolic dynamic, we prove symbolic dynamics in these energy changes in arbitrary directions. They can move up, down in any prescribed fashion. We have estimates on the Hausdorff dimensions of orbits that go through these energy changes. And we can also prove some results about stochastic nature of these energy changes. But I certainly don't have time to go into details. Thank you very much for your attention.
Thanks, Maciej. Fantastic. Anyone want to start the questions? Anyone have any questions from the talk?
Well, I have a question.
Please, Michael.
Yeah.
So in the construction of the map sigma, which is the basis of the shadowing map, you started with the point x and then went backward in time to get the point x minus and forward in time to get the point x plus, and then define sigma of x minus is x plus.
Yes.
But this x where you start from doesn't appear in the map sigma. So couldn't it happen that if you start with with two x values, and going backward in time, you end up with the same x minus,
Yes.
but going forward in time, you end up with different x plus, and then that mapping
Yes.
would not
Yes.
be well defined.
The answer is yes. This scattering map is not uniquely defined. You can have 2, 3, infinitely many scattering maps. And the shadowing lemma that I've mentioned is fantastic because you can also compose different scattering maps. So there's a lot of freedom of choice. But the answer to your question is yes, you are 100% correct. The scattering map is not uniquely defined, and you
But
can
it's actually a set-valued map, right?
yes.
Yes.
So sorry, what set valued?
Yeah, so what I meant is, but that for one x minus, could you have two different x pluses? So
But
Yes.
you pick
Yes,
one, and
but
then
you
have a nice
you
map.
pick one.
you just
So
okay. Just,
you pick just one, and then so in principle, what I could have is I could have another point x plus here. I could have another fiber, and I could have another intersection here.
yes.
This would be another scattering map. Another thing that can happen that this map could be undefined. So you can have ranges where you have x minus and you have x plus, that you have these intersections of fibers. And maybe, possibly, in some other regions, the scattering map is not defined. The fibers don't intersect.
Right.
These sort of things actually happen and are a little bit unpleasant. But where you can actually define a scattering map, you can use it for this shadowing lemma. So in fact, what I could be doing is I could be working with a couple of these scattering maps and composing them in different orders. And in fact, I would still be able to shadow this type of pseudodynamics.
Okay, so that means that the choice of that sigma does not influence the results. So in a sense, you get a different orbit then. But
it definitely will be a different orbit, but an orbit will exist that will move close to this pseudodynamics.
Yeah, so that means in principle, when you have various sigmas, then you can also, by this lemma, you get various orbits.
Yes, yes. And using different scattering maps is useful, because what you want is you want the scattering maps to be constructed in such a way that you increase or move in the energy in the direction that you want. So maybe one scattering map is not going to do it, but another scattering map is. Okay. So you choose the one that is in your favor.
Thank you.
So Maciej, what you discussed is just at the end the work with Gidea, okay? But you listed like 5 authors. So what is your current project, let's say?
Okay, so with Raphael, the story has started, and we wrote a paper about like a Melnikov type approach, but we didn't convert it to computer-assisted proof yet. Okay, I think I'm on a great slide. And with the remaining authors, what I'm working on, and what is in fact very close to completion, is the computer-assisted implementation of this shadowing lemma technique with computer-assisted proof. So this is the rest of the authors.
So you do rigorously this scattering map?
Yes. Yes, we do this rigorously. But we don't do it in the setting on celestial mechanics. We have a toy example, which is for maps. But I think that the step to celestial mechanics is a small one.
But you play with conditions, etc., right? To define the point on the.
No, this is a different. I mean, the question is, okay, how do you compute the scattering map? And we use two methods. So we have an example in which the scattering map is computed with parametrization method and with conditions and covering relations. We show that, okay, this methodology is, I mean, the way that you compute these fibers is kind of your own business, right? The methodology will work for both, or maybe there are other methods for computing these structures.
So I have another question, which is maybe a bit technical. So the constant C, which is visible on the slide, which is you're just showing, you compute it by the derivative with respect to epsilon of h. But what does it finally depend on? Is it does it depend on the sequence xk or and nothing else, or on what does it depend?
So we are talking about the explicit construction, yes?
Yes.
This one. So in fact, the assumptions are as follows, right? For every horizontal disk, I can do this construction. But in a computer-assisted proof, you do like, let's say, a finite sequence of these. We call these connecting sequences. Yes. So for one horizontal disk, you need one connecting sequence, another you need another connecting sequence, and so forth. So we have to explicitly construct them. Once you construct them, for each of them, you can compute this bound on the derivative, but there's a finite number of them. And then what we do, okay, let's choose the C to be the smallest one.
Okay. Yeah.
So all these conditions, there's a finite number of them.
And can it happen that by a bad accident that you can't prove it's positive?
Yes. So the bad example is a resonance. So let's say that I don't, because we're talking about a map, right? So let's say that I have a situation in which I return exactly at the same angle. But if I return exactly at the same angle, I have to expand in the theta coordinate, right? So if I have identity, I'm always expanding. I'm never going to fit these guys. So the resonances are the enemies, but this happens in many methods, right? And it can happen that you can't do it. But the thing is that if you have normally hyperbolic manifolds and you have intersections, there are going to be plenty of these intersections, right? So you have these primary intersections, secondary intersections. If things move about, and typically you would have to be extremely unlucky for this, at least in theory, not to work. But that is, you know, theory, and then the brutal fact is that you have a system for which you need to do computer-assisted proof, and things, of course, never cooperate as well as you would like, right? So there are many difficulties, but a definite difficulty that will kill you is like a resonance, one-to-one resonance.
But fortunately, the computer-assisted proof method tells you if that happens or not. So
yes.
You don't need to bother about in practice.
Yes, but and the thing is that if you have a family of these periodic orbits, let's say talk about this particular example. So there's a bad resonance for you for one, so you can just move to somewhere else where things will be better for you.
Maciej, do you have some picture? Because these conditions that it increases, okay, it does not hold for every angle, let's say, right? There are some regions where this derivative.
Yes, so I don't have the pictures here, and the fact is that so this is a Hamiltonian system. So typically you would see something like this. If it increases for these angles, so you have a change in energy going up. For angles that are like a shift of by 1 pi, you're going to decrease in energy. So in some regions you go up, right? This condition. In some regions you go down, which is useful if you want to do changes up and down in energy. But I don't have a not in these slides, and yeah. To find slides that would be, I don't know. I have pictures. The answer is yes, but not ready at my fingertips.
Because probably during this transition along this chain of covariant relations, okay, somewhere, I mean, this H might be decreasing, okay, but the total effect after you came back to this M is that you got increased, right?
Yes. So let me say the following. In fact, whether you go up or you go down, the main factor that determines it is where you position your, let's say, first window in some sense, right? Because we know that this unstable manifold will wrap around and then you'll have another intersection, right? And that's a different type of homoclinic orbit, right? So if you choose the other one, it will probably do something different, right? But if you choose this homoclinic orbit, right? So you go here and then you come back, what you can do is you can kind of close to the normally hyperbolic manifold, you can iterate as many times as you want because hyperbolicity is in your favor. The worst that can happen, you have to increase the neutral coordinates, right? So, but these iterates that you do close to the manifold, they don't influence the changes of the energy. The change of the energy is influenced by the excursion, right? So if you choose your excursion or you choose your homoclinic orbit in your favor, then things will work fine. If things don't work, you can choose some other homoclinic orbit and maybe then they will. So what I'm trying to say is the following. If you make iterates close to the normally hyperbolic invariant manifold, this will not influence this a lot.
But so my comment is that it's not that this, what is in this, I don't know, ramka? How is ramka in English?
Box.
Okay, this is kind of automatic, okay?
No.
You have to carefully choose the, in your picture, this will be the angle more or less and energy level, right?
Yes.
To have it happen, okay? So this is like, so this is where some heuristics and empiric approach enters, okay, to construct things, okay?
But if you want to have a more automated method of finding out how to choose different regions where things are going to be in your favor, what you can do is you can use the classical perturbation theory, because the perturbation theory will tell you, okay, you have like you compute your Melnikov integral, you don't need to do it rigorously, right? And from the Melnikov integral computation, you will see, okay, from these angles, I should be going up, from these angles, I should be going down, and you get this information, and then you can do these boxes. So, or you can do it explicitly, or I don't know. But the answer is yes. You do have to be very careful, and you need to do your numerics correctly. It's not that this condition is going to appear just, and it's going to be satisfied. You have to be, in some sense, fortunate to have this. But then again, the system is Hamiltonian. So in the regions where, if there are regions that go down, there are going to be regions that go up, right? So this thing will happen.
Maybe I'm not sure if that's the same context, but is on a general level, I ask myself, is there any natural reason why in such a perturbed Hamiltonian system, the energy can only go up via perturbation? Can it not go down?
Typically, it will go in both directions. So there will be, let's say I have a box M. So probably if I place a box somewhere here at a different angle, then I will be going down.
So why did you never consider this case?
Oh, we do. We do. So we, in fact, in the paper that we have with Marian, what we do is we do symbolic dynamics, movements of up and down. So we have two of these regions. One region goes up, another region goes down, and we ensure that we have connections between these two regions so that we can use both.
I see. So you did it in the paper, but just not.
Yes, it is. No, not. I mean, I barely made it. So some choices.
Yeah. Okay.
That I made.
Okay, any final questions for Maciej? Well, if not, Maciej, I want to thank you again on behalf of myself and the other co-organizers and the audience. And thanks for a wonderful talk this morning.
Yeah, and thanks
Thank
for
you
the
very much.
introduction. The introduction
Thank you
was
very much.
fantastic. I heard often Arnold Diffusion, but I never really got a grip on it. And thanks for doing that. Yeah, I learned something. Great talk.
Thank you.
Thank you.
Okay, everyone. Well, thanks for coming today, and we look forward to seeing you in the coming weeks.